Hi everyone, welcome to lecture 8. This is Intro to Machine Learning. In this video, we'll talk about multiple linear regression, which is also known as multivariate regression. Essentially, we'll talk about mathematical interpretation of multiple linear regression. So how can we express it mathematically? A solution approach to solving that problem, which is the gradient descent algorithm. And then finally, we'll see the Python implementation of multiple linear regression. Okay, so we have looked at the linear model, which looked something like this in the previous video, right? So there was one dependent variable and one independent variable, right? But in real world, we deal with more than one independent variable that impact my dependent variable, which is y here, right? So accurately modeling that is essential for good predictions. So essentially, we are looking at predicting y when more than one variable impacts y. So for example, x1 plus x2 plus x3 and so on. So there could be like more than one x's, and then each of them multiplied by some coefficients, for example, beta 1, beta 2, beta 3, and so on. So this is precisely what multiple linear regression looks like. Let's look at a problem. Okay, so I have this house pricing data, and the link to that is given in the description below. So I have the number of bedrooms, bathroom, the square feet living, and the price of each house, right? So I have to create an algebraic relationship, assuming that there is this linear relationship that exists between the number of bedrooms, bathrooms, square feet living that impacts my price. So my price is y, and these are my x1, x2, and x3, right? So assuming that the three independent variables, which are my x's here, are linearly related to the price of the house, my first observation would essentially look something like this, right? So 2,21900 is some coefficient times my x1 plus some coefficient times my x2 plus some coefficient times my x3 plus a constant, because we saw that in the linear regression part where this was the intercept, right? So some value for 0 when all the x's are zeros, and then obviously an error term, right? So this is how I can express the very first observation. Now this is the equation for linear regression model or the multiple regression model. And with appropriate parameter values, so with appropriate beta 1, beta 2, beta 3, and so on, I should be in a position to come as close to this actual value when I'm predicting for some unknown problem. For example, I have a house that has some attributes like 4 bedrooms, um, 2 bathrooms, and my square feet is 1200. Based on the information that this data provided, I should be able to predict what is the asking price that I should put maybe the listing price that I should put my house on. And that is possible when I know the values of beta 1, beta 2, and beta 3. And that's the whole goal of solving this multiple regression problem, right? But just remember that no model can be built to perfectly mimic reality. So there will be some error, which we are capturing using this term E1. So essentially my model will have each of these observations as a line. So for example, the next line is going to be 538,000 equals beta 1 times x1 plus beta 2 times x2, and notice like this x1 x2 is different for different observations and so on, right? So if we think about these different lines for each observation, we can represent this entire data set, right, in a matrix form, right? So let's write the matrix representation of these vectors, right? So y, which is my dependent variable, is the prices of the houses that I have. So this is my y. For example, the first one was 221900, if I remember correctly. The second one was 538,000, and so on. And so I'm representing it as a column vector, as you can see, right? Similarly, I can express x as all the actual values of my x's, right? So for example, 3 bedrooms, 1 bathroom, and then 1180 is the square feet. And then remember there was this beta 0, which we call the intercept in linear regression. So that exists, that has always, it has the coefficient 1, right? So I'll have this matrix of each observation. So this was 2.25, 2580, and so on, right? So this is my x. And then finally a vector of all my parameters starting from beta 1, beta 2, beta 3, and beta 0. Again, I'm expressing it as a column vector, and my error term, which is, sorry, E1, E2, and so on up to En. N is the number of observations or the size of my data, right? So essentially I can write this matrix as an equation, which is x times beta plus E. Now notice this multiplication here. This is a matrix multiplication. So when the number of columns of the first matrix is equal to the number of rows of the second, then we'll get the exact equations that we had in the previous slide. Now also notice that we have this error term, which can be rearranged to look something like this, right? So this error is a function of my parameters, which I am after predicting, right? I have to predict these to get the price of a house whose price is actually unknown, right? Now, in simple words, we need the model parameters in such a way that we have this error as small as possible. So using this, we'll have the predicted values of, or let's say, a given house, and this is the actual price, right? And we want to bring the actual and the predicted as close as possible, and for that we'll have to minimize the error, right? One way of doing that is to express this error as mean squared error, and that's one common way of doing when dealing with regression problems. So my mean squared error by definition is the sum squared, just like we did with the ordinary least squares with linear regression and multiple regression. I write it something like this. So I is from 1 to n. N is the number of observations. This is the data size. And then E squared, right? This summation EI squared, error squared, can also be written in matrix form, because we know that if this is a row matrix, and so on up to En, and if it's multiplied by a column matrix, E1, E2, and so on up to En, I can write it as E transpose E, and so on. And so I can substitute the value of here, because E is y minus x beta. I can substitute that here and get this mean squared error as 1 over n times y minus x of beta transpose times y minus x beta, right? So for transpose it's this thing, and without transpose it's this thing. So essentially, using some identities, we can further simplify this expression. I'm not going into the details of that right now, but all I'm trying to emphasize on is that this is the cost function, right? And cost function means that this is my error term, which should be minimized such that I get the best model parameters. That means the beta vector. And remember, the beta vector has the values beta 1, beta 2, beta 3, and so on, right? So my cost function has to be minimized. I have to get the error term as small as possible, so that and so that I get some model parameters that minimize this, right? And in order to do that, we use a technique called the gradient descent algorithms. How does that work? Now, I know that this mean squared error, and we have seen that in the ordinary least squares as well, is convex. So essentially, if in very simple terms, you can look at it something like this. So the gradient of the mean squared error, which is the differential, essentially can be calculated, and that's always a convex function, right? So we are trying to find the gradient, which is nothing but the derivative of the mean squared error with respect to each of the model parameters. So basically, I'm trying to find the partial derivative of this mean squared error with respect to all the model parameters, right? Beta 1, beta 2, beta 3, and beta 0. And once I have that in the form of a vector, right, I can use the gradient descent algorithm. And just to give you an overview of how this works is that, let's say I find the gradient, which is nothing but the derivative of, and this is my error, and this is just like one of the parameters, right? Obviously, we are dealing with more than one parameter, but I'm just like simplifying it to make you understand. So we'll begin with some initial haphazard value of beta. Let's say this parameter is just beta 1, right? So I'll just begin with, let's say beta 1 is 0, I don't know. And then I see that my error is somewhere here, right? And notice I'm trying to minimize the error, so I'm trying to reach to this lowest point. And how do I do that? So I begin with some beta, initial beta, and then I calculate the error and I see that there is a lot of difference between the actual error that I'm getting, that I'm trying to get to, right? So what I'll do is I'll update and create a new beta based on the values that I have. So whatever the old value was there, right, minus some learning parameter times this differential value, right? So this differential value, I am just denoting it by a j, right? So this times j, or let me write it down clearly here. The new values of the parameters will be something like this. The old one from where I started, and then minus alpha and times j. Okay, so what's happening is this is just like one step. We have to keep repeating this step and updating the values of my parameters until I reach at a point when my error cannot be minimized any further. So that points to the fact that I've reached somewhere here and this was my goal. And so I'll take that parameter, whatever that value would be here. Right, so this is the whole idea of gradient descent. This here I illustrated it using just one parameter, beta 1, but obviously that's not the case with our problem. So that looks something like this, right? And the steps are shown here. And as you can see now, this is a three-dimensional 3D figure, right? So we're looking at two more parameters. So for example, this was our beta 0 and beta 1 because we're calling them beta. And this is my MSE or my error, right? So again, we're trying to minimize it. Let's say we begin here, right? And then using that formula where we were updating beta old, beta new is old minus alpha, which is the learning rate or the learning parameter. This is nothing but some number, right? So this gives the magnitude of how much we want to go down, as you can see, right? And then the delta, which is my j or the derivative. And this in every step or in every iteration will take us to the minimum point. So as you can see, initialize the parameters. Step 2 is calculate the gradient, which is the differential, and then change the mean squared error. And again, adjust the weights with the gradient to get the optimal value, and then keep going. Use the new weights for prediction and calculate the new mean squared error, and repeat 2 and 3 until you see that the error does not reduce significantly, right? So this is how gradient descent algorithm works. Okay, and this is how we solve the optimization problem for multiple linear regression. Now, with this, we understand the mathematical interpretation as well as um, the gradient descent algorithm. Let's go and look at the Python implementation for this. Okay, so let me keep this. Let's go to Spider. And even before we begin writing the code, just let me show you, this is the housing data that we've looked at before. What I have done is I just copied the price because this is our dependent variable, and then some of these independent variables here, bedroom, bathroom, and square feet living. And I copied that into a new Excel, which is, excuse me, this looks like this. Okay, so I'm reading in that, and all the data has been copied from the previous videos. So all of this is the same. I imported the libraries, imported the data set, created the test and training set split. And here notice I'm training my model. And this is very similar to what we did with linear regression. The good thing here is that this linear regression class in Python helps us create the multiple linear regression model as well. And um, a common question is what happens to feature selection? So for those of you not familiar with feature selection yet, we'll talk about it in one of the later videos. But essentially it's to look at which model features or parameters are more important than the other. And there are many techniques to deal with that, right? Linear regression class actually comes built in with that. So it'll take care of that. So all I'm doing here is creating an instance of my class linear regression, just like we did with multiple linear regression. I just named the variable multi-regressor, and then I did a fit with the training set, right? Now, obviously, this is 4 dimensions. This has like 3 features, right? And one dependent variable, so I cannot visualize this. But we can definitely look at we can predict the results, obviously, right? So the first thing that I'm doing is creating a variable called y underscore pred, and that equals whatever the name of my variable is, which is multi-regressor. And then the method here is dot predict. And what do I want to predict? I want to predict the values for the test set. And that's exactly what I'm doing here, right? The next thing is I want to check whether how close the test set predicted values are with the actual values, right? So this is something that we definitely want to do. And here I'm doing exactly that, right? So print, and what I want to do is I'm using the numpy concatenate function. So np dot concatenate, here it comes. What I'll do is I'll concatenate the predicted and the actual test values, and then I'll reshape them so that I can look at it as a column vector. So in order to do that, what you have to do is, as you can see, the first argument is the tuples that you want together, right? So what are those tuples? I'm going to specify them now. So concatenate, and then the tuples are y underscore pred dot reshape. So just like for formatting, and what do you want to reshape? Length of the same array, which is y underscore pred. This will be an array, right? And then what should be the axis? Just come out of this and a comma and a 1, right? And then come out of this. The next one is going to be y underscore test dot reshape, and then the same thing like we did here. So essentially give it the parameter length of itself, which is y test, and then come out of that, comma 1, and let me see, 2 more parentheses, and then comma 1 for the actual concatenate, right? So that's that, and let's actually run this entire script to see if this works fine. Okay, so it's running, and okay, so it's still running. Let's see what's the outcome that we get. Okay, so here we have the predicted and the actual values, as you can see, and then there are a lot of values after the decimal point. So I can take care of that by doing something called, I'll show you with NumPy, you can set print options, right? So if you do set print options, you can specify your precision. So let me do that. So precision equals 2, and then let me just run this part of the code now. Okay, so we can see the values, not a lot is clear, but you can see some of the predicted values are close, some are really far off. One important usage of the model that we created just now would be to predict for a certain house. Let's say I have a house and I want to predict using the attributes, the input values, I want to predict how much that will cost, right? Based on the model that I created, because that was the whole point of creating this model, right? So multiple regressor, that's the name of my model, and obviously I want to predict, and I should have a two-dimensional array here. So for example, the number of bedrooms is 3, 2 bathrooms, and then let's say the size is 1200. According to my model, the value or the price for that would be around 292K based on the model that I created, right? So this is the Python implementation for multiple linear regression. And with this, I end this video.